Alright, so I think this is recording, or at least I hope that it is. Let's take a look at problem number 5. We've been looking at, in this skill packet 4, at polynomial functions. And eventually we're going to get to a point where we want to sketch the graph of a polynomial function. We've taken a look and we know the end behavior, and we know how to find the y-intercept. It's just a constant term. This graph has a y-intercept of 18, but for these higher order polynomial functions, when we say higher order, higher degree, when that degree starts getting above 2, 3, 4, 5 and stuff, we needed a method to factor in order to find these x-intercepts, and this rational zero theorem was our answer. It's a nice tool, and we use the remainder theorem and the factor theorem and our knowledge of synthetic division to help us completely factor these. Now, always look and see if you have a greatest common factor. So for this one we do. So I'm going to come in and do that first before I start looking to see what my factors of my leading coefficient and my constant term are. So I don't have a variable that's common to every term, but I see that every one of these numbers here are divisible by 6. So I'm going to rewrite this f of x as 6 times x to the 4th plus 2x cubed minus 4 times x squared minus 2x plus 3. So hopefully I haven't made a silly arithmetic error. And now I'm focusing my attention on this polynomial, this factored polynomial. Now, when I look at the constant term of 3, I'm interested in the factors of 3, which are just 1 and 3, positive or negative 1, positive or negative 3. The leading coefficient is 1. Well, that just has factors of 1. My factors of my constant term are going to be in numerators, and here the leading coefficient, its factors, are my possible denominator. And I create a list, and there's no guarantee in this list that any of these are zeros of this function. I don't know yet if this graph crosses the x-axis at all, intersects the x-axis at all. But if it does intersect the x-axis, and at the number that it intersects it, if that's a rational number, then it should be in this list of either positive or negative 1 or positive or negative 3. So now, by either plugging in these values into the function and looking for an output of 0, or what I'm going to do is just synthetic division to look for a remainder of 0 to see if I can factor this any further. So let's try positive 1. Now, when I look at this, it's in standard form, and this time, in the past, some of these problems had missing terms where I had to put a 0 in there. Well, this is 4, 3, 2, 1, and a constant. I don't have to put a 0 in there. So let's see what this remainder is. I'm hoping, I'm in search of remainders of 0. We found one right off the bat, so that's kind of nice. Now, I can see with the 1 and 3 and negative 1 and negative 3 that I will be able to factor this by grouping. And I did that in a previous problem. But suppose I don't recognize that, and all that I recognize is that this is now a third degree polynomial. Well, it still has, ignoring the negative sign, it still has the same list. The leading coefficient of 1 has factors of plus or minus 1. The constant term, the negative 3, has factors of positive or negative 1, positive or negative 3. It generates the same list. In fact, the 1 might be a 0 for this. So let's check that. This could be a repeated root. Let's check and see if 1 is a 0. If we pull 1 down, multiply by 1, 4, 3, 1 times 3, 3, and it is. Okay? So now This one was of third degree. This one is of second degree. So now I know that my factoring, my X method or the quadratic formula can take care of this. So if I want to stop my synthetic division, I can do the rest from my previous knowledge that I had before ever coming to the class. So I've got f of x is equal to 6. Remember, we factored that out. And this guy had a factor, had an x-intercept at x equals 1. And in fact, I've got x equals 1 repeated. So I'm going to write x minus 1 times another x minus 1, which is just x minus 1 squared. So then the 143 gives me 1x squared plus 4x plus 3. So if I set this equal to 0, and if I solve this equation, it's going to give me all the zeros of this function. This guy I can factor to x plus 3 and x plus 1. So I can divide both sides by 6, and this 6 is canceled. It does not contribute towards an x-intercept. Multiplying, 6 times 0 is just 0. So, I can cancel this 6 out. I'm just going to get it out of my way by dividing both sides by 6. Now, 1 minus 1 is a 0. Negative 3 plus 3 is a 0. And negative 1 plus 1. Now they want me to form a table. Now remember, these are my multiplicities here. So I have 3 zeros to write in my table. Let's write my table over here, and I'll even change colors to hopefully make it easier for you to read. The zeros of this function, we found 3 of them. We've got negative 3, we've got negative 1, and we've got positive 1. The multiplicity, well, at negative 3 we had a multiplicity of 1, and that's an odd number. At negative 1 we had a multiplicity of 2, and that's an even number. And at x equals 1, here we had a multiplicity of 1, and that's odd. So these multiplicities help us in determining, does the graph cross the x-axis or does it do a touch and turn? So we're interested in how, we'll just call it, intersects the x-axis, and it intersects it with an odd value, that it crosses the x-axis. With an even, it does a touch and turn, and I'm going to abbreviate touch and turn as TNT, and here across. So if I add up these multiplicities, it should, it most often will add up to the degree of my equation. Now, if I had some complex numbers, it'll be a little bit less, like we saw in a previous problem. But here, 1 plus 2 plus 1 is 4. We have found all of the x-intercepts. We have identified how the graph crosses at each of these zeros. So we're done, and I hope this helps, and I will talk to you later. Bye.